London and University College London, founder and co-director of Tanuki Technologies and leader scientific and engineering consultant at Imperial College Consultants. So, welcome, Ado, and looking forward to your exciting presentation. Here you go.
Thank you. Thank you for a kind introduction. And yes, my name is Ado Farsi, and I'm currently the co-founder and managing director of Tanuki Technologies Ltd, but I'm also a researcher at Imperial College London and University College London. And the title of the talk that I'm going to present today is Bridging Computational Mechanics and Machine Learning in Geomechanics with Insights for Subsurface Engineering. And thank you again for the invitation to deliver this seminar at this webinar. So let me just move this. Okay. This talk is going to be divided in three parts. So the first part is going to be about a model reduction for borehole stability. The second part is about digital twin for simulating fluid flow in westerly granite. And the third part of the talk is about a novel framework for embedding neural networks, machine learning models, into PDEs and solve them with finite element method. So without further ado, let's start with the first topic, which is titled Carbonate Rock Failure and Solid Production, Onset Rate and Volume Predictions. This research was done in collaboration with PETRONAS, a Malaysian energy company, and was done in collaboration with John Paul Latham and Rob Zimmerman from Imperial College London. So let's introduce the topic. So what's solid production? Well, solid production is when you recover solids in a production well. So, and it could be caused by wellbore instabilities, a failure of borehole completion, collapse of some sections of the well, and could also be induced by drawdown seepage forces. The factors that cause this solid production are stress redistribution around the borehole, different properties in the rock and fluid in the reservoirs, type of completion that are used in the well, and the drawdown pressure. So it can have bad effects like unwanted effect on the production because of pipeline erosions. Downhole cavities can generate downhole cavities, can even generate blockage of the perforations or the production lines, and most importantly, if this happens in a production well, it can require separation and disposal of the solid at surface, which is very costly, and it must be avoided. So the way we tackled this problem was by developing a combined finite-discrete element method that can estimate the breakdowns of the solid in the well. So what's the finite-discrete element method? Just a very quick overview. So it has, as like the name says, it has both finite and discrete element method. So the finite element method is basically deals with the deformability of bodies. So your simulated body is discretized with finite element, and so you can compute the deformations, stresses, strain in the body. Between each finite element, we have what we call joint element that you can also imagine as a cohesive element, if you are familiar with that side of the literature. So we have basically a law that defines when there is a separation allowed between elements. And when this separation happens, you have fracture propagation in the solid matrix. And then the DEM part of the method deal with the contact interaction between particles. So when you have different, for instance, different fracture walls or fragments, even fragments that are moving in the domain after they've broken into pieces because of in situ stresses, for instance, We can deal with we can track the displacement of these particles, and we can deal with the contact interactions between these particles and other particles or the other walls of the domain. So for instance, here you can see a simple example. You have this borehole. You have some fractures propagating in the wall, and you have some fragments detaching from the wall. So all of this can be dealt with this framework. And yes, I don't have time to go too much into the details, but I'm open to answer questions if you have any more questions about the framework. And this is also being, so FDEM is also being coupled with the pore pressure. So basically, we needed a way to define the pore pressure into the reservoir around the borehole. So I created this one-way coupling, assuming that the pore pressure is known and it's just a function of the distance from borehole walls. And then we coupled this into like the framework of pore elasticity into FDEM. Numerical validation, I'm gonna skip it because I don't have time to go through it, but I'm open for questions. And then the experimental campaign. So for this particular project, as I said, we were collaborating with PETRONAS, and they were interested in solid production in carbonate rocks. So carbonate rocks can have very different properties depending on the porosity of the sample. So we defined a test routine in order to characterize all of the properties, for instance, the tensile strength, Young's modulus, and other properties that are needed in our computational tool as a function of the porosity. And then we also needed to validate our model, and the test that we selected for the validation of our model is the advanced equal cylinder test. So for the people who are not familiar with this test, you basically reproduce the conditions of the borehole well in a small scale in the lab. So basically you have a cylinder and you drill a hole, which represents your well, and then you apply some horizontal confinement stresses, vertical confinement stresses, and you can also apply differential pressure between the inner borehole and the outside of the cylinder. In this way, you replicate the condition in the well, so you can study different drawdown pressure and in situ conditions. And for instance, here you can see a sample before testing and after testing. And after testing, obviously, because of the in situ or like the boundary conditions, the confinement and pore pressure that have been applied to the sample, you have that some parts of the wall have broken into pieces, and so you had some solid production in the lab. So we used indirect tensile strength. Sorry, we used Brazilian Dis test, triaxial test, and UCS test to optimize the strength parameters and Young's modulus of the samples, and trying to optimize these properties for different porosities of carbonates rock. And then we used, as I said, some advanced equal cylinder test for validation. And obviously you need to, you have the test, you run the test in the lab, and then you need to set up a simulation that represents the conditions in the lab. And that's what we did. We characterized the properties of the specimen that was tested in the lab. All of the properties then need to be fed into our numerical tool. We apply the same boundary conditions, and we check whether we were matching the simulation, with our simulation results, whether we were matching the experimental data in terms of solid produced against confinement pressure. And we got a pretty good match, especially in terms of onset and value of production after onset. Some snapshot from the simulation. For instance, at this particular phase of the experiment, you have that some of the solids start to break from the wall, and you also have some fractures that propagate inside the specimen, but still they do not close up, and so they do not form fragments that can be moved by the fluid flow. And then you increase the pressure. This fracture propagates further, but still they are still just fractures. They are not forming fragments. And then after like a bit another increase in confining pressure, you get collapse of the sample as we were testing in the lab. So then the nice thing of computational mechanics is that you can repeat
it's
the
going to take a
test.
while, but
You can repeat the simulation for different conditions and different properties of the rocks. So here in this table, you can see that on the x-axis, we change the, on different tables represent different strength of the material. So imagine different values of porosity of the carbonate rocks. And then on the x-axis, we have different ratio of vertical to horizontal stress. And then on the y-axis, we have different ratios between the drawdown pressure and the confining stress and the in situ stresses. And you can see that for different combination of loads and or these parameters, we get different results in the solid production. And then we run several simulations, like hundreds of simulations, and we parameterize the simulation and interpolate the results. And we created a reduced order model to that can be used with a graphical user interface to understand, to predict whether a particular section of the well with particular rock properties and in situ conditions and drawdown pressure is gonna have solid production, and if so, how much solid is predicted to produce. And then we use a blind test. So once we had our tool, we received some data, field data of some samples. And then we tried with our numerical tool, and we saw that the solid produced for just a meter of this of a section of the well of this with these particular conditions was generating 1.19 kilograms of solids. And it's interesting to know that what they recover at surface was 3.3 kilograms, but the section was around 3 meters. So it was a pretty good match. So in conclusions, we develop an effective computation of this rock mass under the effects of steady state fluid flow and in situ stress confinement. The results from the proposed FDEM methodology of 3 different scenarios were compared to simulations obtained from Farajik, which this is the validation, numerical validation that I skipped in this talk. And the mechanical tests were conducted to characterize and test the advanced pulse cylinder samples of carbonate rocks with different degrees of porosities. The test results have been used to produce correlations between the carbonate porosity and the mechanical properties of interest. This is the experimental campaign that I showed you at the beginning. Combined finite-discrete element simulations of advanced thick wall cylinder tests have been validated against onset of solid production and the cumulative curves of solid produced in the experiment. As I shown you, we have a very good match. And we developed this graphical user interface that has been used by engineers in PETRONAS. So it was a pretty successful research that we conducted. Now I'm gonna jump into the second topic of my talk, which is about developing a digital twin of westerly granite to investigate fluid transport and heterogeneity during fault evolution. So motivation of this work, obviously faults in tight crystalline rocks have higher hydraulic conductivity than the rock matrix. This is well known. But the current understanding on the permeability of rock faults relies on static measurements that are taken either before or after faulting. So the space and time evolution of permeability during this faulting process is yet unknown. So with this work, we wanted to provide an accurate three-dimensional determination of the evolution of permeability during fault growth and answer the following questions. At which stages in the faulting process does the permeability undergo the most significant change? So the difference at the time evolution of permeability, and how heterogeneous is the permeability along the shear fault. In other words, the heterogeneity of permeability in the fault. And in order to answer this question, we developed this very sophisticated experimental apparatus. I forgot to mention, apologies. This research was done in collaboration with Nicolas Brandtut and Franz Eben. And Nicolas Brandtut is a person who developed the research, who developed the pioneer of this methodology to obtain pressure measurements in different locations in the sample during the triaxial test. And Franz Eben is the person who actually conducted the experiment that I'm going to present right now. So basically, we had to develop this very sophisticated experimental apparatus to extract pore pressures heterogeneity measurements, acoustic emissions, and obviously stress and strain measurements during a triaxial test, and conduct some flow test. But I'm going to explain this into the details with this slide. So a sample was initially confined at 85 MPa, and during loading, the pore pressure was maintained at 5 MPa, and the axial load is applied at constant shortening rate. So you can see here the shear stress against equivalent fault slip, which you can also see as the vertical displacement of the vertical confinement punch. And then this experiment, this triaxial experiment, is posed at 23 stages. And during these 23 stages, we do a flow test. We run a flow test. What's a flow test? Basically, here is our sample. We apply a differential pore pressure at the top and the bottom of the sample so that the fluid is forced to flow from the top to the bottom. And then we have different pore pressures, transducers, sorry, that can measure the values of pore pressures at different locations, ideally 8 locations on the 2 sides of the sample. So we can measure both the pore pressures at different locations in the sample and the flow rate. This is like the differential pressure is 5 MPa during the flow test. And then another important thing to highlight is that we are including 2 notches in the sample so that we force the fracture to propagate, the fault to propagate at a particular angle in the sample at 30 degrees. And another important aspect is that we were also monitoring the fault with acoustic emission sensor, these orange sensors. That allows us to extract the acoustic emission during the test, which allows you to understand where the fault is propagating in the sample. So, for the simulation framework, so the forward problem, we solve mass conservation equation and RC law for an incompressible steady state flow. You can see the equations here. So we assume a permeability of a bulk of 10 to the 18th meter squared, and this was based on previous experiments on the same rock. And then we assume that the permeability of the 2 notches is 3 orders of magnitudes higher than the permeability of the rock. This to assume that it's almost void in these zones. And then we rescale all of the quantities in the experiment, in the simulation, so that we can obtain values of boundary conditions at the top of 1 and at the bottom of 0. and a flow rate at a reasonable scale. And then we reproduce the exact geometry of the sample using Gmesh. So we have the two boreholes that induce the two pressures at the top and at the bottom, and the notches, etc. Then for the inverse problem, we assume that the fault is propagating over a thickness of 1 centimeter, and this was based on the measurements on the post-mortem sample. We could see the extent of the fault on the sample. And then we assume that we discretized, the permeability in 10 cells. So each cell has an individual independent permeability. And we monitor the evolution of this permeability in each cell. So the unknown of the inverse problem are indeed the time coefficient of each cells. So the 10 permeabilities of each cells. The observable are 6 values of pressures because 2 pressure transducers stopped working during the experiment, and the flow rate. The objective function was defined as a summation of the square residuals of the difference between the observed and measured pressures and flow rates. And then we use an adjoint method to compute the gradients of the objective function with respect to the 10 coefficients. And we use BFGS to calculate to minimize this objective function until we optimize these coefficients. And we use pi-adjoint and Firedrake basically to do this optimization problem, this inverse problem. So to give you an example, let's focus on one of the stages of the triaxial test halfway through the test, so stage 15. So we have these measurements of pore pressures at the different transducers. We have this value of flow rate. So the optimization process is ask questions: what are the different permeabilities in the different zones the fault, so that we match exactly this value of flow rate and this value of pore pressures. And so using this inverse problem, we can optimize these permeabilities. And this is the result of the simulation. So you want that, this is the simulation output with this values of permeabilities. So basically, you want that the flow rate represented by the flow lines in blue here matches the flow rate of the experiment, and the pressure represented by the pressure field represented by the equipotential surfaces here generate a pressure in the sample, so that the pressure recorded by the transducers is exactly the same as the pressure in these locations where the red spheres are in this plot. So if you repeat this process for all the 23 stages of the experiment, you can optimize the 10 independent values of permeability for each stage. So you have a time and space evolution of permeability during faulting. Let's first focus on the time evolution. So let me just move this a bit. So for equivalent fault slip, so at the beginning of the experiment, of the triaxial test, we have a very sharp increase in permeability. And so in the order of 150 times the original permeability, the bulk permeability of the sample. And as I said before, we were collecting the acoustic emission density. We were collecting the acoustic emissions of the test, and that we could use to extract the acoustic emission density field, which is what I'm plotting here, which give us an idea of the damage in the rock. So where the fracture has propagated in that at that particular stage of the experiment. And this data set is independent from the data set that was used to optimize the samples. So it can be used as sort of a validation of our methodology. So we can see that in this initial stage of the triaxial test, we have two to basically branches of fractures propagating from the top notch and from the bottom notch, which highly increase the permeability of the rock, but still the two are disconnected, so there's still improvement in permeability that can be done. Then in the next stages, we have a plateau. And if we analyze the acoustic emission density field, we can see that although the damage zones are expanding, the two zones and all of the damage zones are still highly disconnected. So they do not contribute in an increase in permeability. Then we have a sharp increase for equivalent full slip just above 0.6 millimeters. And if we check the acoustic emission density field in these particular stages, we can see that it's exactly when the two main fractures are connected here in the top part of the fold. And then again, we have a plateau. So the the permeability doesn't increase much. And that's, again, we can see from the acoustic emission density field, we can see that there is a small expansion of fault zones, but they are already connected. And so there is not much to be gained with it. Let's now focus on the heterogeneity. We can see that cell 10, so the portion of the fault here in this corner, experience a very large increase in permeability when compared to all of the other cells, especially to the cell on the left-hand side of it. And if we observe the acoustic emission density field, we can see that in that particular location, there is a high concentration of damage when compared especially to the portion of the sample on the other side. So it makes sense that the flow of fluid wants to pass through that cell, let's say cell 10, and so that particular cell has higher permeability. And then if we observe the permeability of cells 6, 7, 8, and 9, they have a lower permeability compared to the other cells. And again, by observing the acoustic emission density field, we can see that although there is a large amount of damage in that zone, the damage zones are highly disconnected when compared to for instance, the damage zones on the other side of the fault. And this justify the fact that we are measuring a lower permeability in these particular locations in the fault zone. So to conclude, we were able to identify stages during the faulting process where the permeability undergoes the most significant changes. We were also able to determine the extent of permeability heterogeneity along the shear fault zone, revealing a variation of up to 8 times between the different zones in the fault volume. And then we identify some future work that I don't have time, unfortunately, to cover. And finally, we get to the last topic of this talk, which is titled Universal FEM-based Learning, embedding neural networks into PDEs as trainable operator for scientific machine learning. And this work is done in collaboration with Nassim Boziani and David Ham from Imperial College London from the maths department. And I'm particularly proud of this work because I think that this something novel and that can be very useful in many branches of science and engineering. So most of the theory for this framework has been published in this preprint. You can find it here, but most of the results that I'm showing now are in a manuscript that is currently in preparation. So this framework is based on Firedrake and Phoenix, which are finite element package that allow you to basically, to cut the story short, to define any partial differential equation. Basically, you can automatically generate finite element solvers for any partial differential equation. So any problem that is described by partial differential equations in a very easy way. And then it does all of the magic to generate an efficient parallel finite element solver. I don't have the time to go much in the details, otherwise I would have shown you an example, but if you are interested, you can use a QR code to go on this Colab Jupyter Notebook and try yourself some examples of Firedog to solve an elastic problem. But what's the main idea of the methodology that I'm proposing? So imagine that you have a problem where some parts of these problems are known. For instance, you have, in the example that I'm giving you next, we will have that we know that in a solid, when you deform a solid, you know that there is conservation of momentum, you know that there is equilibrium of forces if it's a static problem, you know maybe the boundary conditions, the geometry of the solid, etc. But then there are some portions that might not be known. For instance, you don't know the constitutive model that describe the relationship between stress and strain of this particular material that you are deforming. And the idea is that you can represent this portion, this operator in your PDE, for instance, the constitutive model, as a machine learning operator. And normally the standard approach, once you have you want to use a machine learning operator to represent something like that, you would need a lot of data of the input, a lot of data of the output of your operator, and then define a loss between the input and output of your operator and your data set, and fine-tune the parameters in your machine learning until the output matches your training data set. The problem with this, when you want to train some operators in this way, is that some operators don't have a measurable output. For instance, in the case of the constitutive model, whilst the strain, which is the input of the model, is a measurable quantity, the stress is not measurable. So you end up with the impossible situation of having to train your model with an output that you cannot measure. With like constitutive models, we try to use simplified loading conditions so that you can idealize your model so that you can assume that you know the stresses. But still, for some other problems, you might not have this luxury. And in another important aspect is that you need a lot of data because in most cases you need to say that you want to use a machine learning model to simulate the whole process. So not only the constitutive model, but give you the deformation of the solid during this process. Under some other conditions, you need to give data so that it can also learn all of the physical laws. Whilst with this methodology, we can use the prediction from an FEM solver that has a machine learning model embedded in it, and use this prediction to train the embedded model, to define a loss to train the embedded model. Now, let me go into an example. So in this example, we have that the physics that we want to, so we have let's start with the experiment. We have a compression experiment. So say that you have your rock and you do a uniaxial compression test in a displacement controlled fashion. So you apply a displacement and you measure the load with the load cell in the experiment. So you have in your experimental data, you have a bunch of data of imposed displacement and imposed displacement and loads recorded during the test. And also this experimental data give you a lot of other information about the problem. For instance, the geometry of the sample that is tested, the governing equation, the fact that it's a static problem, so you can apply equilibrium of forces or stresses, and you know that it's small deformation, so you can use this definition of the strains. And then you have that some portion of this governing equation, sigma, which is your constitutive model, is described by neural network. And what you want to do, you want to optimize the parameters of these neural networks using something that you can measure, which is the force that is given in output by the FEM solver and the measure force that you have measured during your test. And with this framework, you can do this. You can use this data to selectively just train not the whole model. So you don't need to train make the model learn the geometry, the governing equation, boundary condition, but just the part of the model that you don't know, the governing equation. And this allows you, so for instance, in this example, I'm using just 6 values of force to completely train a constitutive model. So here you have the force displacement in output from our FEM solver after 10 training loops, and it's obviously off. In the dotted line is the ground truth, imagine your experimental real data set. And then during training, we can change the parameters of the constitutive model until the FEM solver returns the correct values of force displacement curve. In this case, a material softening curve, so a rock with a softening low. And this is done just with 6 values, 6 scalars, 6 values of forces. Why is it possible to do that? Again, because with this framework, we are very selective. So we can use the data just to train the part of model that we don't know. And I give you another example. Imagine a Brazilian disk test, which is a common test does in rock mechanics to estimate the strength, the indirect strength of rocks. In this experiment, we do it in load control. So we applied a load and we measure the displacements. Imagine that you have a digital image correlation technique that you can use to recover the displacement field. So the displacement of all of the material point of the sample for each applied load. So in this case, again, we want to find the constitutive model. And instead of using forces, we used the experimental displacement fields and the displacement field that is given in output from the FEM solver with this embedded machine learning model. And again, here we are able to train this model with just 6 fields of displacements. And we here you can see an example. So since the ML constitutive model is agnostic of the type of constitutive model that this material is at the beginning of the training, could be anything. It thinks that it's a sort of gelatin. So after 10 training iteration, it largely overestimates the deformation of the sample. But let me explain to you. So the red contour represents the simulated deformation at that particular training stage, and the dotted line are the real deformation of the sample, so the ground truth. And after 100 iteration of the training, so after epoch 100, we have that the model has completely learned the constitutive equation of this material and can exactly reproduce the amount of deformation. And then the other interesting aspect, I'm aware of the time, I'm gonna take another couple of minutes. Another interesting aspect is that once you have learned this constitutive model in an experiment, you can just take it and change the other parts of the abstraction. So for instance, instead of simulating a Brazilian disk test, now I want to simulate a 3D plate with a hole that is under a torque, and use exactly the same constitutive model that I trained with Brazilian disk test. So I can extrapolate and reuse my learned constitutive model, in this case, my machine learning model. And for instance, here you can see an example. This is the most constitutive. This is the synthetic experimental data results of mean stress. And this is the results given by the ML, the constitutive model that was trained with the Brazilian disk data set. And you can see that it's exactly the same stress field. And this test is particularly tricky because it's torsion, so we go from tension to compression within the thickness of a sample, and also there is a hole, so there is stress concentration. And then finally, very quickly, you might say, well, you're training a model just with 2D examples. What about more complicated equations or more time-dependent equations in 3D? Can you use this kind of simulation to train your model? And the answer is yes. For instance, here I want to learn a nonlinear conductivity of this particular material, which is a 3D plate with this very complicated geometry, and it's actually a two-body problem. So that I have a copper plate with a known thermal properties, this complex shaped plate with unknown thermal nonlinear thermal properties that I want to learn. I use the temperature field of an experiment to learn this constitutive model. This heat conduction model. And here is the results, the data set that we're using. So we have an oscillating boundary condition of temperature on one side, and so there is a change of temperature in the whole domain, and in particular in the plate that I want to of which I want to find the nonlinear heat conduction model. Obviously, the geometry is complicated, so there is a hole behind. So the temperature field is quite complex, also given by these tortuosities. Nevertheless, we are able to learn this nonlinear heat conduction model. So here you can see in red our machine learning model after 10 iteration is trying to learn this dotted line. So after 50 is approaching closer, and after 100 epochs has basically learned the nonlinear law in this particular interval of temperature, which are the temperature used in the experiment. So in conclusion, I have presented a model reduction example for borehole stability, an example of a digital twin for simulating fluid flow in rocks, and lastly, this very novel FEM-based learning that is about embedding a machine learning operator into PDEs and solving them with finite elements. I thank you for your attention, and before I end my talk, I just wanted to very quickly talk to you about the company I'm directing. So it's Tanuki Technologies Ltd, and we offer consultancies for engineers firms that need very sophisticated simulations that are not currently available with tools that they have. So we try to bridge the gap between academia and industry with very advanced simulation tools. And we offer consultancies, but also customized software tools as a service. And in particular, these tools run on the cloud, and we are particularly strong in simulating fracture propagations and fluid flow in porous medias, and also in integrating artificial intelligence with computational mechanics simulation. So with this, I end my talk, and if you have any question, I'm happy to answer.
Thank you, Ado. Thank you for the very interesting talk. And I think we already have comments on the questions in the chart.
Okay, let me
open the chart
see.
and start to address the questions.
If I can open the chat. Okay. Simplest. Okay, so the first question is about the wellbore stability.
Did you see it?
Sorry, it's a pretty lengthy question. Let me just read it. So
Yeah.
a simple positive
It's
model for
pretty
this
long.
condition would seem. Okay. So to answer this question is actually yes. So when we were doing the so in the part of the talk that I had to skip because of the time, as I said, I ran validation with FEM solver that obviously being a continuous FEM solver cannot model fracturing as FDEM. And so I was using exactly this approach. I was just comparing the value of stresses and see whether the value of stresses were going above a certain strength threshold, for instance, of tensile or of shear given by a more Coulomb failure envelope. So this is. So then we have another question about the third paper. Have you tried using technique to evaluate hydraulic boundary condition or hydraulic flow? So, but to answer your question, no, I haven't tried, and I would be very interested to try if you have any of this data set. So let me answer the last question. Yes. So to answer your question, it can also capture post failure. So the approach that I've covered here. Let me just use the presentation to answer this question. So I've shown an example with this machine learning model that represents a constitutive model. You can have a machine learning model that represents the failure envelope, for instance, the failure conditions, or you can have a machine learning model that represents the post-failure behavior of a material. So since it's using Firedrake, which is a very how can I explain this? It's a very basically the only thing that you need is to have a mathematical expression that include that you can include in the Firedrake package, and then you can basically use a machine learning model to represent any other operators in your problem. So to answer your question, yes, you can. But if you have more specific questions about how to implement this, I would be very happy to answer, like if you drop me an email or a message.
Okay, great. So from the audience, is there any questions?
I had a general question about the theory or like behind the model itself. So the strength in your model, is it like 1 point, or is it like an actual strength envelope, or yeah, how does strength work?
In which in the model sorry, which one of the three we're talking about? The first one
In
was
general, like the capability of the model itself, more like, yeah, can you,
okay.
yeah.
Okay. So for what concerns the the first model that I've shown, so this FDEM model. So it's a failure envelope, like here. I should have a slide with some, yeah. So we can, like, since you simulate the stresses in each point, you can have a definition of the stress, a strain, etc., and you can then check whether the stress are greater or smaller than a failure envelope. In this particular case, we have a tensile cutoff so that we can simulate tensile strength and failure in tensile, and we have a shear failure envelope defined by cohesion and an internal friction angle. For what concerns the third part of the talk, it's very general. So whatever you want to implement, for instance, if you have a phase field, a fracture problem, you can then have a machine learning operator that learns when this phase field is gonna give you failure in shear or failure in tensile.
And this failure is like a stress-based criteria, or how does it work? The strength failure, yeah.
So in this particular case, it's like failure is a stress criterion. So you measure stress at the joint elements nodes, and so depending on the amount of stress, the nodes then release an amount of stiffness. So they start being very stiff. So it's like there is no cohesive elements or joint elements between elements. And then when the stress reaches a certain value, for instance, the tensile stress reaches the value of the tensile strength, then you have opening allowed. So the joint element loses its stiffness and there is an opening, and so there is a tensile fracture. And the same thing in shear. So for this particular model, for FDEM, that's how we describe failure.
A final follow-up question. So how does the computational cost of your FDM compare to something like a traction separation based model, or like a phase field model? Like how does it compare to like conventional fracture models?
That's a good question. So FDEM is pretty intensive in terms of memory and computations, because it's describing not only the failure, but also the possible interactions of the fragments. So that's why in terms of how fast the code runs compared to, for instance, a phase field, probably FDEM it's a bit slower than a phase field code. But on the other hand, a phase field code cannot simulate what I'm showing you, what I'm simulating here. Once you have fragments, so a fracture that completely break a portion of the domain, with a phase field model, you cannot simulate the displacement and the motion of these fragments, whilst with FDEM, you can do that. So there are pros and cons. I would say that it's a bit slower, but if you need to simulate some phenomena like fragmentation, then you need this type of simulation tool, because you cannot do it with a phase field model or any other model that it's a continuum model.
Thank you.
Thank you.
Any other questions? Actually, there's some suggestions from the chart. I think you can have a look.
Just
new suggestions. Bangaran Alexander.
The solid production model from your first paper. Well, Alexander, if you want to drop me an email, I would be very interested in getting involved if we want to write a proposal. I think that obviously this can be a very interesting application. So yeah, just drop me an email and we can see whether we can write a proposal. Thank you for the suggestion, Maria.
Yeah, about the new question about the recording, we have a YouTube channel. We will put the past seminar recording on our YouTube channel. Yeah, not only this year, you could find the past seminars in the last year, also in our YouTube channel. Yeah. I think I will try to touch in the chart. Yeah. Oh no, I think I just sent to one person. Sorry for a mistake. To everyone, anyone who is interested can access our past recording via the YouTube channel. Thank you. And actually, I also have the questions. So from the first paper's work, my understanding is you switch on not only the normal model 1 and model 2 for the fracture. Is that correct?
Yes, that's correct.
Okay, that is why I see the shell fractures around the wellbore. Yeah. So
yes.
Very interesting.
Yeah, in fact, the way these carbonate rocks fail is mostly because of the in situ conditions and the pore pressure, the bottom hole pressure. It's basically just mode 2 shear. I mean, they initiate in mode 2, but then obviously, you have a wing crack and then the closing portion of the crack is mode 1, but the initiation is mode 2. So you need to implement a shear failure in order to characterize these breakouts in.
Yeah, and actually it also depends on the problem you want to analyze. And also for the machine learning, I think it's a very great idea to incorporate the machine learning. Actually, I used to do some work like collaborating with a machine learning group and try to train the machine learning model to predict the complex fracture, hydraulic fracture and propagation. But I think we did face a problem when trying to train the machine learning model. I think it's like the model works pretty well, matching the past, matching the history. But when it starts predicting the future time, how the fracture will continue to propagate, it does has problem. So do you have some comments on or have some idea based on the experience? Yeah.
Yes. So I can point you to our paper, our preprint, where we have actually shown that with our methodology we can predict. So if you check this preprint, we use a fluid flow problem. So we simulate a Navier-Stokes equation, classic problem of flow with an obstacle, and there is an example of machine learning models used to reduce the FEM model that simulates the Navier-Stokes, and we're able to train the model and then use the model to predict times that are beyond the time that we use to train the model. So we have an example where we can actually use the machine learning to learn the actual physics in order to allow the model to be able to extend the prediction. So not only give you back the training data and the context of the training data set, but also extrapolate the physics to learn how to predict the next steps of the fluid flow or different Reynolds numbers in that particular case. So yeah. And the other point that I want to make, that I want to stress, is that with this approach, if you have a machine learning model that only needs to care about some part of the physics, and the other rest of the physics that you actually know is described by governing equations that are fixed, that don't need to be trained, then you are also more, you have more security of the fact that the model is going to be able to predict situations, scenarios that are not containing the training data set. Because if this changing in scenarios can be correctly described by the physics that is described like hard coded in the FEM model, and then the abstraction of the ML model needs to be very limited, because it's just limited of a portion of the model is responsible to simulate, to represent, and all of the other physics is already hard coded here, so it doesn't need to be learned. So my personal opinion, obviously, I would need to show like examples of this, is that with this particular approach, you can have models that are more reliable for predicting scenarios that are outside the training data set.
Okay, yeah, thank you so much. Okay, so thank you everyone for attending this seminar. So have a nice rest of the day. Bye-bye.
Thank you. Thank you for inviting me and for joining the seminar. And again, if you have any questions or you want me to drop me an email, I guess you can find the email at the beginning of this. Are you going to share my email, by the way? If not, let me see if it's here. I should have my email at the beginning of the talk. No, I don't have my email. Anyway, my email is just my name.surname at imperial.ac.uk. Or you can just drop me a message on LinkedIn. I have a LinkedIn account, Ado Farsi. So I'm really happy to answer your questions, or if you have any idea for collaborations, it would be very interesting to know about it. And thank you again for the invitation.